Today we're going to try to standardize across all normal distributions, and in particular we're going to look at this concept called z-scores and how that'll help us in calculating percentages associated with these normal distributions. So let's get started, and we begin with talking about the standard normal distribution. So the standardization process, we have the standard normal distribution. It's just a normal distribution with a mean of 0 and a standard deviation of 1. So we're going to try and draw this thing real quick. And if you recall, we have our normal distribution, so it's a single peaked bell-shaped curve, and it's completely determined by its mean and standard deviation here. So we have the centerpiece where it's 0, and then we can draw each standard deviation. So for 1, 2, and 3, that's 1, 2, and 3 standard deviations away from that mean. And then we can go on the other side, -1, -2, -3, that's 1, 2, and 3 standard deviations away on the left-hand side from that mean. And the purpose in doing this is trying to generalize our old-fashioned mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, and then on the other side mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma for our general normal distribution. So we're trying to fit this type of curve into that standard normal distribution. That's our main goal. And our way to make that transition is this concept called z-scores. And so if x is just some observations from that normal distribution with a mean mu and a standard deviation sigma, then we can form the z-score of x just by taking z equal to x minus mu, that whole quantity, divided by sigma. Now what this is doing is actually standardizing our curve, so turning it into a formula for the standard normal distribution. So we take any old curve, let's once again have our mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, and then on the other side mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. What we have is this mu, this center point. If we convert that to the standard normal distribution, that becomes z equals 0, regardless of what mu is. So mu could be 1,000,000, mu could be -5. Regardless, when we use a z-score concept, that's z equals 0. So we're standardizing that value. The mu plus sigma, notice it's 1 standard deviation away, so that's going to be actually z equals 1. And the mu plus 2 sigma, notice 2 standard deviations away on the right hand side, so the positive side, so that's going to be z equals 2. Mu plus 3 sigma, something similar, we're going to get z equals 3. And then if we go to the left hand side, mu minus sigma, that's going to be z equals -1. Mu minus 2 sigma, we get z equals -2, and mu minus 3 sigma, we get z equals -3. So let's try and work an example out as to how all this comes together. So looking at this example, the average normal core body temperature for a human being follows an approximately normal distribution with a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.4 degrees Fahrenheit. And we want to find the z-score corresponding to a person having an average normal core body temperature of 97.8 degrees Fahrenheit. Well, taking a look at this problem, we know we want to find a z-score, so that z equals x minus mu, that whole quantity, divided by sigma. Keeping that in mind, we can find some of the values pretty easily, and the mean stares us right in the face here. If you look right in that position, this gives us mu equals 98.6 degrees Fahrenheit. And in a similar manner, we have the standard deviation right next to it. So standard deviation sigma, that's 0.4 degrees Fahrenheit. So now all we need to do is find x, and we can get our z-score. So x is actually equal to 97.8 degrees Fahrenheit, and you can see that because we're talking about a person having an average normal core body temperature of 97.8 degrees Fahrenheit. So if we plug this in, we get z equals x minus mu divided by sigma, and so our x is 97.8, our mu is 98.6, our sigma is 0.4, so that gives us -8, or -0.8, excuse me, divided by 0.4, and that's z equals -2 when you carry out that calculation. So for our next problem, we want to use the empirical rule to find the percent of the population having an average core body temperature of at most 97.8 degrees Fahrenheit. And notice that number matches identically from part 1. That won't always be the case, but in this case it is. And for that reason, we can use our z-score. And we use z-scores on standard normal distributions. So if we look at a standard normal distribution, let's draw that out here. We can have our mean, if this is our standard normal curve, we have our mean being 0. We can go to the left, -1, -2, -3, and then to the right, 1, 2, and 3. But remember, on a standard normal curve, our mean is 0, our standard deviation is 1. So, by the empirical rule, we know that 95% of the observations lie between -2 and 2. So, with that in mind, we got to think about, first off, we have that information. What are we actually looking for here? We're looking for, if it's at most 97.8 degrees, that means at most the z-score is -2. So that means and I'll shade it in right here. It means we can just look at the values from -infinity all the way up to -2. And that'll give us our value that we're actually looking for. So keeping that in mind, though, if we have 95% on the inside between -2 and 2, that means outside of that, so from -infinity to -2, and also 2 to infinity, we're going to have 5% total. So we have 5% total where those arrows are going, right? But if we have 5% total left, we have two different positions, and this is symmetric. So we know we have two sides we have to account for. And if that's a 5% total for those two sides, that means there's 2.5% on each side. Well, notice that answers our question, because on the left-hand side is the only part we were looking for. So that means we have 2.5% of the population has an average core body temperature of at most 97.8 degrees Fahrenheit. And this gives us an idea of how to work these types of problems, just using the empirical rule. As long as our z-scores line up as to one of those values, we can always make that calculation.